So today we are going to cover groundwater. Groundwater makes up 0.6% of all of the world's water. The source of groundwater is precipitation that sinks into the ground. Sinks into is also known as infiltrate. So groundwater is water that fills open spaces in rocks, sediment, and soil beneath the Earth's surface. When precipitation infiltrates the ground, it seeps downward into spaces called pore spaces. These are some examples of materials that you can find underground. Rocks and groundwater will fill in fractures, cracks, and air bubbles if you're talking about volcanic rock. But that's basically where the groundwater can be found within rocks. You can also have loose sediments, and then groundwater will fill in the spaces between the sediments, like pebbles and sand. And then also you can have soil underground, and then the spaces between the soil particles will be able to fill in with water. There are different factors that affect infiltration, or how much water will sink into the ground. This is in a comparison to water becoming runoff instead of seeping into the ground. So these are some factors: climate, and that's your temperature and your precipitation. That's what climate is, precipitation and temperature. So temperate and tropical regions receive more precipitation than dry areas. So there's more potential for infiltration. Slope of the land. Steep slopes, you're going to get more runoff and less infiltration. Soil and rock type. For example, pebbly soil can absorb more water more quickly than clay-rich soil, because clay hinders the infiltration. It doesn't allow water to pass through as easily. Vegetation. Plants absorb water and lessen runoff. Land use. That's referring to if areas are paved over with concrete or pavement versus if land is just grassy or a forest, let's say, with just lots of plants. And then the degree of saturation of the ground. Saturated land cannot hold any additional water, so the excess becomes runoff. Not all earth materials are equal in letting groundwater pass through. What types of earth materials would be the most efficient at allowing groundwater to pass through? Clay, pebbles, sandy, clayey, pebbly mix. How do we answer this question? We look at different properties to consider how to answer this. How much space is available within the material? That's called porosity. And how easily does water move through the material? And that's called permeability. So porosity is the percent of a material's total volume that is pore space. In other words, it's a measure of the empty space between particles. So here is a table that shows you the porosity values for different materials. So this part of the list shows unconsolidated sediment. That's just referring to loose sediment that's not cemented together. It's not a solid rock. So soil has about 55% porosity. That means if you have a cup full of soil, about 55% of that cup of soil is actually empty space. That's what that means. And then that empty space can actually fill in with water. And then here's a list of rocks, and the porosity of different rocks. So these are examples of porosity in bedrock. So if you have well-sorted sedimentary rock or also unconsolidated sediments, those are going to have high porosity. If you have, let's say, a sandstone, for example. Poorly sorted sedimentary rock or poorly sorted unconsolidated sediments have a low porosity because the smaller pieces are filling in those pore spaces. In soluble rocks such as limestone, porosity can be increased by solution. Now, what does solution mean? Solution is when calcite in limestone is dissolved by rainwater. Rainwater is actually naturally slightly acidic. And then you have, let's say, metamorphic or igneous rocks that may have fractures. Those fractures are going to lead to the porosity. And then we have factors that affect porosity of loose sediment. Pretty much the same thing that we were just talking about in terms of the sorting. So well-sorted sediments are going to have a high porosity, and poorly sorted sediments are going to have low porosity. Porosity is highest when all the sediment class are equal in size. That's going back to the sedimentary chapter in terms of when we talked about what well-sorted and poorly sorted means. And again, the poorly sorted sediments allow the smaller pieces to settle into the pore spaces. So you're taking up space that otherwise water would have filled in. The space is being filled in with smaller sediment grains instead. Okay, so that's sorting. Now what about shape? Particle shape. Rounded versus angular. So rounded particles, you have better porosity. Angular particles, you have less porosity. And the reason for that is the angles, the edges of the angular particles fit more compactly together, filling in the pore spaces, kind of like puzzle pieces, where the rounded pieces, as close as you can get the rounded pieces to touch each other, there's still going to be spaces in between because of the rounded edges. Porosity does not depend on particle size, however. So here are some examples of particle sizes. And this is shown in diameter in centimeters. So 0.9 centimeter diameter, right? That's larger particles. These are smaller particles. Because these are all well-rounded and well-sorted, they all have the same porosity. Okay, so porosity is not related to the size of the particles. Then we have permeability. Permeability is a material's ability to allow fluids to pass through. In other words, how easily water can pass through a material. Factors that affect permeability include porosity, the size of the pores, and the interconnections of pores. So for size of pores, the larger pores leads to more permeability. So for example, clay has a low permeability because the pores are tiny. Pebbles are more permeable because they have larger pore spaces. And the interconnections of pores is the degree to which the pores are connected. For example, pumice has many pore spaces, but they're not connected. They're not like tunneled together, like they don't connect. An aquifer is a permeable layer beneath the surface that allows groundwater to pass through easily. An example of an aquifer would be a well-sorted, well-rounded sand, for example, sandstone, or just a pile of sand. I'll add that here. Sandstone or sand deposits. And gravel as well. Okay, so sand and gravel. Limestone that has fractures enlarged by solution are also going to be a good aquifer, and we will talk about that later. An aquiclude or an aquitard is a layer that prevents groundwater movement. It's impermeable. And this includes shale, many igneous and metamorphic rocks, clay layers, and volcanic rocks. So this diagram shows you zones beneath the surface related to groundwater. So first you have the rain. Water is infiltrating from the rain. It seeps downward into what we call the zone of aeration, and eventually will accumulate in the zone of saturation. The zone of aeration is a zone with some air. So many of the pore spaces still contain air. Suspended water is water that stays behind, stuck in between some of the soil particles, or the whatever particles are down here, sand, gravel, or soil. So little bits of water are going to stick in between the particles and remain. So that's suspended water. Okay, again, the zone of aeration, most of the pore spaces contain air. The zone of saturation is where the water ultimately collects, and that's going to have all the pore spaces filled with water. Now, the boundary between the zone of aeration and the zone of saturation is called the water table. Now, if we take a closer look at the water table, the boundary between the zone of aeration and the zone of saturation, you have little molecules of water that start climbing upward into the dry areas of the zone of aeration. And that happens through capillary action. That's because of water tension. So if you were to look at the side of a glass of water, you would see little tiny area where like the water looks like it's climbing up the glass. That's the same thing. It's the water tension. So we call that little area where the capillary action or the water tension is causing water to rise upward a little bit from the water table. We call that the capillary fringe. So this just summarizes the previous figure: the water table, the zone of aeration, the zone of saturation, and the capillary fringe. Now you can model the capillary fringe, capillary action, by taking a paper towel and just putting the edge of the paper towel in a little dish full of water. And then you could watch the water rise upwards into the dry material. So how does groundwater move? Groundwater moves downhill due to gravity, but it's moving underground. Also, the groundwater moves from areas of high water pressure to areas of low water pressure. That's called the hydraulic gradient. This is why water would pour out of a water balloon if you make a hole in it, because outside the water balloon is low water pressure. Inside the water balloon is high water pressure. So the water is moving towards the low water pressure outside of the water balloon. Velocities of groundwater movement average a few centimeters per day. So groundwater moves slowly. It's not fast like a garden hose. It's like a slow movement. And then this shows underground. The blue is the water in the zone of saturation. And you have a river valley. So the water is higher in the areas where the land is higher, because when it rains, the water is going to be closer to the surface there. So you get high pressure because it's a higher elevation of the water table. And then this is the low pressure. So that's your water is going to move from the high pressure to low pressure. So the water is moving downhill and it fills in the river. So part of this river is filled in with rainwater rainwater coming from like up in the mountains at the beginning of this river, but also some of this river is being filled in with groundwater. And then here you have a clay layer and then a little water table on top. That's called a perched water table. And then because this is a hill, part of the land intersects with this water table, and then that's going to cause springs. So that's just water that's like trickling out of the ground surface downhill. So now we can talk about groundwater withdrawal. So discharge is any process that lowers the water table. There are different causes of discharge. When groundwater flows into streams, lakes, or swamps, it becomes surface water, so it's no longer groundwater. So that is, you're losing groundwater because it becomes surface water. And then springs, as I just showed you here, and wells. Recharge of groundwater is when water is added to the groundwater supply. So recharge comes mainly from precipitation. Rain or melting snow would be the examples of precipitation. To a lesser extent, we have things like septic tanks and something called recharge ponds, which allow groundwater to recharge. So this is what a spring would look like. And again, you have perched water tables, and then you have the ground surface intersecting with the water table, and then the water just like comes out of the ground. So that's a spring. And here on the right is a photo of what the spring would look like. There are some areas, you're not really going to see this too much on Long Island, Queens, and Brooklyn, but if you go like upstate or you go somewhere else, sometimes there's like rocks on the side of the highway and you see like water trickling out of those rocks. Those are springs. And this is a well. This is the simplest form of a well that you could possibly have. It's a hole that you dig into the zone of saturation, and then water seeps into the hole. So in this case, this woman is collecting water from this hole that was dug into the ground, deep into the ground until they reached the zone of saturation. Now you can dig a well at the beach. If anyone's ever gone to the beach, sat down in the sand and dug a hole, you may have reached water, like at the bottom of the hole. And that basically is the same thing as a well. Now, groundwater exploitation means that groundwater has been exploited or used up rapidly or more rapidly than it could be recharged by precipitation. And the long-term effects of this exploitation have not really been thought through. So this has led to the lowering of the water table, or something called cones of depression, saltwater intrusion, land subsidence, and contamination. So then I will go through each of these. So lowering of the water table is due to overuse of wells, where you withdraw groundwater faster than it can be recharged by precipitation. So an example is in the middle of the country, you have what's called the High Plains Aquifer. And this is 2 to 100 times more water is taken out of the aquifer than is recharged. So the water table is dropping in many areas within the High Plains Aquifer. So if we look more closely, the colors here, the High Plains Aquifer water level change in feet from 1980 to 1995. So increases in the water table, that means there's more water, that the water table got higher because you added water, okay? But the oranges and the yellows and the reds are a decline in the water table. Now, when I said you added water, I mean like this, let's say just rainfall patterns may have changed, or maybe there was less groundwater taken out in those areas, allowing the water table to rise again. That might be. There are different factors. Okay, but the decline in the water table is typically due to using more of the groundwater than what is able to be recharged by precipitation. So the lightest color yellow is showing 5 to 10. That means the water table has dropped 5 to 10 feet between 1980 and 1995. Okay, and then like the dark red here is more than 40 feet. And then the really dark, like brownish red, is where you have areas of little to no saturation. So it's like just pretty much dry underground. So we do actually have quite a bit of those areas as well. So you have this whole section of oranges, reds, and browns, or whatever this color is, maroon. Those are all areas where the water table is dropping. And again, that's because they are using more groundwater than what is replenished by rainwater. Now, if we look, let's say, southwestern Kansas, you have a lot of the area has shown a decrease in the water table. So when I looked into that, it seems that there's a lot of farming, like cattle farms, livestock. So that requires a lot of water. Okay, a lot of farming in that area. So let me just zoom in. Whoops. Let me zoom in So you can see on the bottom, it says drought, as seen here in 2012, is a constant concern for anyone living in Kansas, particularly those involved in agriculture. Drought can shave billions of dollars off farmers' balance sheets and devastate communities, but irrigation can make the difference between survival and losing it all. But then you have to have somewhere to irrigate it from, right? Corn and beef production alone, fed by the Ogallala Aquifer, which is the aquifer that you're looking at in this slide, employ more than 56,000 people and add $3.2 billion to the Kansas economy, amounting to 4.3% of its jobs and 10% of the economy. So you have this large portion of the economy of Kansas is related to agriculture, whether it's livestock or farming, like crops farming. So they're using a lot of water, okay? And this whole thing is the Ogallala Aquifer or the High Plains Aquifer, okay? So in the future, if it continues with the amounts of agriculture in Western Kansas, if that continues, they're gonna continue to have a problem with the groundwater there. And then here is California. Groundwater level changes reflect the difference between the spring 2004 and spring 2014 and spring 2013 to spring 2014. So this shows you change in groundwater level. Oh, by the way, if you go to this link, which I have linked on the bottom, if you click the past year versus the past decade. So what I have it clicked on for this image is the past decade. So that's that's 2004 to 2014. But if you clicked on just the past year, it would tell you 2013 to 2014. So this shows you red is a decrease in the groundwater level of 10 feet or more. The orange is 2.5 to 10 feet. And then the yellow is either plus or minus 2.5 feet. So that's not really that much of a change. And then the blue and the green is an increase of the water levels underground. So you can see there are several parts of California where you are dropping your water table. Now, think about it this way. If you have a well, and that's where you get your water from, if the water table drops 10 feet, that means you have to dig the well, depending on how deep your well is dug in the first place, you might have to dig another well that's 10 feet deeper. Or you might have to dig that well 10 feet deeper to reach the water table. Okay, so let's take a 5-minute break, come back at 2 o'clock. Okay, so yeah, I see you're all writing in the chat like, okay. Oh, wait, I pressed record. So like, you're gonna hear some weird thing all of a sudden, like half of my sentence just got cut off. Okay, so groundwater overdraft is when groundwater use exceeds the amount of recharge into an aquifer. You could read more about the groundwater overdraft that's occurring in the Western US at this link here. But generally, it's similar to what I was explaining here in California. So within that topic of overusing wells, we have the concept of a cone of depression. Overuse of wells depletes groundwater and lowers the water table in a cone shape around the well. That is called a cone of depression. Cone of depression in the water table forms when water is pumped out of a well faster than it is replaced. You could see a similar occurrence if you were to drink from a really thick milkshake with a straw. Like if you drink really quickly, around the straw, you would see the milkshake kind of sinking down right around the straw. That's pretty much the same thing as a cone of depression. And if you don't like milkshakes, you could think of it in terms of like a really thick smoothie. Okay, so make a really thick smoothie, put a straw in the middle and drink fast with the straw. Like you will see around the straw, it depresses, it like goes down a little bit. That is a cone of depression. And then if you have wells nearby that are more shallow, they will go dry. And I'll show you how that works in an animation.
Formation of a cone of depression. The water table elevation always decreases around a pumping water well. This happens because groundwater flows toward the well, and the water table surface always slopes downward in the direction of groundwater flow. In this animation, you will examine how the water table is affected by pumping groundwater at different rates from two closely spaced wells. When water is pumped from the aquifer adjacent to each well, the water table elevation drops. This causes the water table to slope inward toward the wells from all directions, so that the water table resembles an inverted cone, which is called the cone of depression. This inward slope causes more groundwater to flow toward the pumping wells. Each cone of depression enlarges in area and depth until the increasing flow of water toward the well balances the amount of water pumped from the well. In this case, the cone of depression around the deep, heavily pumped water well intersects the bottom of the shallower, less heavily used well, so that the shallow well goes dry.
Yeah, if you see where the arrow is right here, it says dry well. See, this well only goes down to this depth. This main well goes all the way down here. So this shallow well is not deep enough to reach this groundwater now that the groundwater has decreased because of the cone of depression from the overpumping from this main well here. Okay, so overpumping of wells can lead to cones of depression, which can cause nearby shallow wells to go dry. And then here's another diagram of the same concept. Then you have saltwater intrusion. This occurs in coastal communities where you get contamination of fresh groundwater with salty water. And the excessive pumping from a well draws salt water from nearby because you're at the coast. The salt water is drawn into wells. And that's actually called a cone of ascension. I'll show you this in a diagram. If you put recharge wells nearby, it can counteract the effects of the saltwater intrusion. So in this case, this is before pumping. Okay, so here's the ocean water, here's a coastal community. There's no buildings in this diagram, but pretend it's a community. This is the water table, this is fresh groundwater, and then the salty groundwater is underneath. The reason for that is because salt water is more dense than fresh water. So the salt water sinks below the fresh water, and they don't mix easily, actually. It's like trying to get oil and water to mix. Like those things don't mix. salt water and fresh water don't mix that easily either. So then you install a well, and then you start pumping. So now, eventually, you might have salt water come into that well instead of the fresh water. And no, you can no longer use that well because now it's contaminated with salt water. Now, if you were to put a recharge well and allow for precipitation to go back into the ground in this area, then you could reverse the effects of the saltwater intrusion, and then you would start pumping fresh water again. Then we have land subsidence. So the removal of groundwater, for example, if you're going to use it for irrigation for growing crops, it can cause poorly consolidated sediments to become more compacted. The dates on the pole show the subsidence in the San Joaquin Valley in California. And that goes back to this map here, where you have areas of California with the groundwater level has been dropping. That's related to a lot of the farming and the irrigation that happens because it's a drier climate. It's not like necessarily a wet climate that's good for farming all year round. It's there are parts of California that are a little drier. So in order to get the water for farming, they take it out of the ground. But over time, that has caused the sediments underground to become compacted together. And it actually caused the land to sink. Okay, so the dates on the pole, this up here is where the elevation of this land was up here in 1925. This land where the guy is standing on, in 1955, the land was at this elevation. And the photo was taken in 1977. So between 1925 and 1977, there was up to 9 meters of subsidence. Let me see the chat here. I don't know if the land has pavement there now or not, but yeah, if they had more pavement, then there would have been even less recharge from precipitation. But again, we're talking about a drier climate. Like here, it rains and or snows all year round. Like it rains, it precipitates all year round, whether it's in the form of rain or snow here where we live. So we have constant moisture throughout the year. Sometimes over the summer, we may have a little bit of a drought, but for the most part, we're in a moist climate. But there are parts of California that are more dry, but they're still farming. So, but they don't necessarily have the water resources that they need. So they pump it out from the ground. It's not necessarily a sustainable way of farming because you're using a lot of water that they don't necessarily have a continuous amount of. So for a short time, the surface water started to be used instead of relying on the groundwater, and the subsidence was reduced. Again, subsidence means that the land is sinking. And then there was a drought between 1987 to 1992, so they started taking groundwater again. And the subsidence occurred again. So for a more updated picture, this is the land subsidence in the San Joaquin Valley between 2007 and 2011. And this is in inches. So the dark blue is sinking of 7.8 inches, and the pink over here is 43 inches sinking. So in the middle right here is where you have the worst of the sinking. Okay, but generally like this whole area you have sinking. And then this picture, it's a sign, a road sign. It's kind of an interesting sign. It's like the car is going to fall into this subsidence area. Okay. Now this is also a more updated version of that pole picture. So let's zoom in a little more here. So the picture was taken in 2013. And on the sign, it shows 1988. So that's where the land was in 1988. Then you have the land in 2004, 2008, which shows you that spot in only 4 years, it went down. You know, you can even see the change over 4 years. And then in 2013 is on the ground that she's standing on. So you can see like the sinking has continued. I don't have like the most recent picture. I don't have anything that says like till 2020 or 2019. But you could see between 1988 and 2013, the land sank another 4.8 feet. Okay, so again, I don't have like the most updated information about the sinking in terms of like a photo of someone holding a pole, but we can look. This is 2011, and then the picture I showed you earlier was 2014. These are the most updated graphs that I have at the moment in the lecture. But if you're interested, you might be able to find some more updated information about the continuation of the subsidence. Again, land subsidence just means the land is sinking. Now also, once you have the sediments get compacted underground, you can't reverse it. Okay, so this is not reversible. This added to this, all of this land, you know, 9 meters, right? 1 meter is about 3 feet. All of this elevation change that they experienced is irreversible. You can't like uncompact all the sediment underground. Okay, and then we have groundwater contamination. The sources might be sewage, landfills, toxic waste disposal sites, agriculture, and natural contamination. And once pollution is in the groundwater, it spreads and then it's difficult to contain it. So here's an example. This is a septic tank. Here is a house with their septic tank. So a septic tank is a tank underground where the used water in your home goes into. This is for people who live in rural areas or areas, maybe suburban areas where they don't have your house may not be hooked up to the municipal sewage system with the sewers and everything. So all of the water that you use, like in the shower, the toilet water, the sinks, all of the water, if a person has a septic tank, all of the water ends up in the septic tank. And then you have these drainage pipes that go out of the septic tank, and eventually water from the septic tank will go into the drainage pipe and go back into the groundwater. That's how that works. So septic tanks can potentially add contamination to the groundwater. Here's another photo, another diagram about the septic tanks. Okay, and then landfills. The part labeled number 1 is a landfill. In this case, it's unlined, but a lot of modern day landfills have a liner underneath that prevents the chemicals from the landfill from going into the groundwater. But in this case, this is unlined. And then it rains, and then the rainwater percolates through all the garbage, and then the water ends up in the water table. And then here's a house with their drinking water well in that groundwater. So potentially their groundwater is contaminated. And then here is a pond, and that pond water is going to be contaminated as well. This is a little story about pollution in an aquifer on Long Island around Bethpage. And the blue line shows the plume number 1, and the red line shows plume number 2. A plume just shows you the extent of the groundwater contamination. So in 1949, chromium contamination was discovered in groundwater south of the Grumman site. Now, Grumman was a factory where they built things like airplanes. So here is an F-14 Tomcat plane that was built on the Grumman assembly line. Okay, so here's the Grumman property. It's right here. Here's Hicksville, here's Bethpage. Okay, so you could read all this information about what happened, but generally there are these 2 contamination plumes underground related to the Grumman factory. And then you also have contamination that seems to be coming from Bethpage Community Park. This shows you how the movement of the contamination happens. So in 1987 that's the extent of the pollution underground coming from the Grumman site. That's 1987. The orange is 1994. The darker orange is 2000. The purple is 2003. And the bluish dark purple is 2012. So if you look here on the previous slide, it's that teal green color is the 2012. So you can see the groundwater is moving southward. So it used to only be up here, and now it's moving southward into northern Wantagh, and I don't know where the boundary lines are according to this map right here, but towards like northern Massapequa and North Wantagh. Okay, then I have another little story about groundwater contamination, and this story is about arsenic. So arsenic can be released to the environment due to coal mining because pyrite present in coal deposits may naturally contain arsenic. High arsenic concentrations can be found in groundwater in aquifers composed of felsic volcanic rocks. So geothermal springs in Yellowstone National Park actually contain, naturally contain arsenic. So I saw a documentary one time, they were talking about like the buffalo drinking from the spring water and they were getting sick from arsenic. But it's naturally occurring from the rocks there. And in Bangladesh, there's widespread groundwater contamination due to arsenic that's present in the aquifers there. So there's been a lot of issues with arsenic poisoning in parts of Bangladesh, but it's because the sediments that are in the aquifers there were like leaching arsenic into the groundwater. Arsenic is present naturally in some rocks. Okay, so then we have sinkholes and caves. And this is all going to be called karst topography when you're talking about caves. So karst topography is topography that results from the erosion of limestone rocks caused by groundwater, and that's called carbonate dissolution. Limestone is a common sedimentary rock. It's composed of calcite, and calcite is easily dissolved by carbonic acid. Carbonic acid forms when carbon dioxide in the air and in soil dissolves in water. So all you need is carbon dioxide to dissolve in water and it creates some carbonic acid. So rainwater and groundwater tend to be slightly acidic. And here is water plus carbon dioxide gives you this combination, which is actually carbonic acid. And you may remember from early on in the sedimentary rocks lab, or maybe the minerals lab, you may have discussed a little bit about how calcite reacts with acid and dissolves. So erosion of limestone and even dolostone, which is a rock similar to limestone. It's also a carbonate rock. So erosion of these rocks creates karst topography. And we call these rocks soluble because they're easily dissolved. So this map shows you the distribution of major limestone and karst areas of the world. So you have major limestone areas, but then the teal blue color is your major karst regions. So that's going to be where you find like a lot of caves. So if you look more closely in the United States, you see in the Appalachian Valleys, Central Florida, you have a lot of karst topography. So if anyone has ever visited a cave, you can think about your experience while you're learning about this here. So different features of karst topography include caves, sinkholes, solution valleys, karst towers, and disappearing streams. So solution valleys form when sinkholes connect. So it's like a large depression. So let's go through all of these. So this diagram just shows you all of those things. So sinkholes are just like little depressions in the ground. And then you have where a line of sinkholes forms a solution valley. Then you have these caves underground. You have this stream that kept cutting downward and downward and downward. So you get these steep walls. And then you have these disappearing streams where surface water in the form of a stream drains downward into a sinkhole, ultimately into a cave. So then it turns into groundwater. So a cave forms when groundwater percolates through the zone of aeration and it dissolves the carbonate rock. Any fractures or bedding planes are just planes beneath rock layers. Those areas are going to get enlarged because of the dissolution caused by the acidic rainwater and acidic groundwater. And then you get these horizontal passages created at the water table surface. This is the water table here. And notice as the dissolution happens, the water table drops. And then this stream is able to cut downward more. You're forming caves and holes underground. So the water table drops even further. You're going to form caves further down, deeper down. And that's because as the river cuts downward into the land, the water table drops. So this river keeps cutting downward. The water table is going to continue dropping. And this is just an enlarged diagram of what's inside of a cave. We'll talk about that in a minute. A cavern is a very large cave or a system of caves. Some examples are Mammoth Cave in Kentucky, Luray Caverns in Luray, Virginia, and Howe Caverns in New York. Howe Caverns is kind of near Cooperstown. It's upstate New York. So dripstones form when water droplets containing dissolved calcite drip from the ceiling of a cave. The dissolved calcite crystallizes back into a solid, and that's a chemical sedimentary rock called travertine, which is a type of limestone. Stalactites are the dripstones that grow downward from the cave ceiling. And you could remember that because the C in the word stalactites is the C in the word ceiling. Stalagmites is when calcite formation occurs on the ground of the cave. And that's because you have dripping from the ceiling and it lands on the floor of the cave. So then you have, it's like an upside down looking icicle, like growing from the floor, going upward. So a stalagmite has the letter G. G is for ground. So stalagmites grow from the ground, stalactites grow from the ceiling. A column is when stalactites and stalagmites meet. A drip curtain forms from droplets that drip down the wall of a cave. And then you also get what's called travertine terraces. So here is a dramatic looking photo of dripstones in a cave. So you have all these coming from the ceiling, you have ones growing from the floor, and then they connect at some point, and then those are called columns. Here are some more dripstones. And then this is like a travertine terrace, kind of, or like a drip curtain. This on the side. What else? If you've ever been in a cave, they usually tell you like not to touch anything because the oils in your finger can disrupt the dripping. So like this little water droplet here, if you were to touch this somewhere up here, the oil like stops the dripping. This is a drip curtain. It's a pretty dramatic looking feature of a cave. but it's like little droplet by little droplet formed this entire feature. Then you can get some minerals that form in caves. For example, in Mexico, you have this one cave or this series of caves in Mexico where crystals of gypsum form, but they're like super humongous. Okay, I mean, look at the size of this man standing here and look at these crystals. This is not a usual occurrence. This just happens to be this area where these humongous gypsum crystals form. Then we have sinkholes. Wait, there's a question. Let's see. I thought that was ice. Yeah, it looks a little bit like ice, but it's actually selenite, which is a form of gypsum. Okay, so sinkholes. That's supposed to be me, by the way. That was like, they had those things, those avatars that kind of like generate their own little cartoons. So there was one at some point that was about sinkholes for some reason. So sinkholes are depressions that form at the surface where there is limestone dissolution beneath. So sinkholes commonly form when underlying limestone dissolves and then the water table drops. So that leaves the cave empty. And then the roof of the cave can just collapse into the cave, leaving a crater at the surface. Sinkholes can also form when sediments above a cave slump inward when the cave roof collapses. So this shows you some sinkholes forming in Florida. So here you have a cavity that forms in the limestone, but the water table is up here. So the water is like holding the cave up because it's like filling in the space. But once the water table starts dropping, let's say you have a drought situation or like you're over pumping wells in the area. So if you were to drop that water table, you no longer have the water pressure holding the cave open. So then you start having sinking into that cave. And then eventually the whole cave can collapse. This is a sinkhole that formed in 1981 in Florida. It formed in previously dissolved limestone following a drop in the water table. So it's 100 meters wide, which is 300 feet, and 35 meters deep. And this shows you areas of sinkholes in Florida. So I just want to point out though, when you go back to this map here, if you zoom in on Florida, Central Florida is major karst region. So you have the major karst region in Central Florida. So you're going to see the examples that I'm giving you of sinkholes are mainly going to be related to Florida. Okay, so here is a map of Florida, and it shows you sinkhole occurrence. So the blue dot tells you a sinkhole happened there and was reported. And then this color red is sinkholes are very few, but several large in diameter and deep sinkholes could occur. So that's this color, this like reddish color. Okay, and then like the more orangey color red, the lighter red is sinkholes are most numerous of varying size and develop abruptly. The yellow color is sinkholes are few, shallow, of small diameter, and develop gradually. Sinkholes are few, generally shallow and broad, and develop gradually is the lightest yellow color, that pale color. So the most dangerous areas to live in for sinkholes are going to be in these dark colors, and then all the blue is where sinkholes have been reported. So it really is in that central Florida area. Okay, you do have the colors show here, but you don't have the blue dots. Okay, so you're looking where the blue dots are and the colors, telling you you're gonna have large sinkholes, some of which occur rapidly. So in February 2013 in Florida, near Tampa, so if you see, here's Tampa Bay, right? Here's Tampa is around here. So near Tampa, a man fell into a sinkhole that formed in the ground beneath his bedroom floor. So this is a photo on the left, looking down into the sinkhole that formed beneath his house. You can see like part of like a floor here, okay? So he actually died from falling into the sinkhole. And then the sinkhole was filled in, but then it reformed in 2015. So I have like these links to these articles. You could read more about it if you want to, but I think it was like 30 feet deep or something like that. It was pretty deep. Yeah, so it's pretty unfortunate, but this is not like extremely common for people's homes to just fall into a sinkhole, but it can actually happen. So I have no idea how like home insurance works with that. I have no idea. Okay, so what is a karst tower? When water sinks into fractures and limestone bedrock, the rock gets dissolved along the fractures and lowers the elevation at those fractures, leaving the rock in between standing tall. So what that means is if you were to take, let's say, a brick, and then if you were to like saw down into the middle of the brick, and then you have like the high parts on the sides, and then it's separated by like the saw mark that you made. It's similar to what's happening here. So water goes into those cracks in rock, and then it like saws down into the rock. So like the top of all of these towers is where the landscape used to be. But then like the water like carved downward and downward and downward as it dissolved the limestone. So then eventually you're just left with what rock is in between the fractures that carved downward. But again, all of these towers are about the same height, and that's all where the elevation used to be. Okay, then we have hydrothermal activity. Hydrothermal refers to hot water, which is heated groundwater. And then it's a discussion of what happens to that water at the surface. So you have something called fumaroles, which are volcanic gas discharges coming from the ground, some of which is steam. That's part of hydrothermal activity. You also have hot springs and geysers. So this is a photo of gases emitted from vents at Yellowstone National Park. And it's related to the magma activity underground beneath Yellowstone. So it's not necessarily a volcano here, it's more related to the magma underground. So hot springs are generally 37 degrees Celsius or warmer. Some of them are even like at boiling point. The heat from hot springs usually comes from magma underground or igneous rocks that are cooling. The western states of the United States have the most hot springs. So like Wyoming, for example. Heat from hot springs can also come from deep circulation and just the geothermal gradient. Again, the geothermal gradient is as you go lower into the ground, it gets warmer. So if you have some really deep groundwater, that could warm up just because it's underground. Here are some hot springs. Some of them get colorful because of bacteria that live in them. Here you can see like this water is boiling. It's like boiling and there's steam coming out. One of the many bathhouses in a place called Bath in England. They were built around hot springs shortly after the Roman conquest in the year 43 AD. So this is a hot spring in England. A geyser is when a hot spring periodically ejects hot water and steam from underground. So it's like groundwater is percolating underground. It's heated, and then the steam and the hot water spew out of the grounds. And this is a picture of Old Faithful Geyser in Yellowstone National Park in Wyoming. It's one of the world's most famous geysers. It erupts faithfully every 30 to 90 minutes, and it spews the water 32 to 56 meters high. So the water at the bottom is at high pressure and high temperature. A rise in temperature or a drop in pressure turns the water to gas, and then it erupts out of the ground. And this cycle keeps repeating. And this just shows you the water underground. It's under high pressure, it's hot, and then it's going to erupt out of the ground. Now in Yellowstone, there's hot magma underneath a lot of Yellowstone National Park. So it heats up the groundwater. And then you get these hydrothermal deposits because the hot spring water and the geyser water contains high levels of minerals and then those minerals are going to precipitate at the surface. So, for example, you can form travertine, which is calcium carbonate deposits. So this is the hot spring deposits in Yellowstone. This is formed from calcium carbonate rich hot spring water that cools and then precipitates the travertine. Travertine is the same rock that forms as stalactites and stalagmites. And that concludes the groundwater lecture.